of the universe. Okay, so the concept is not so hard. Here the mathematics might be a little bit, but concept is easy. So in early universe, temperature was much higher than the mass of any particle. So that means they are called relativistic. Yes, so that means if you take their energy, each particle, which term will remain in the square root? Which term dominates when temperature is much higher than the m? Here, you can tell. P is the momentum. So when temperature is much higher, which term will dominate?
P square, C square.
So E is approximately PC, and that's what happened with the photon. Yes? This is called relativistic limit. For non-relativistic limit, EI is just nothing but mc squared, that you know, the rest mass. This is non-relativistic limit. This will need it later. Now, for example, take a reaction in the early universe, say E plus, the positron and electron, particle and antiparticle. They can come, interact with something, and then go back to photon, gamma. So this reaction is called E plus E minus, goes back and forth with gamma plus gamma. Do you know that in Switzerland, CERN, they collide proton and many more particles get created? That is the normal idea of quantum field theory. You can create new particle by colliding, as long as their charge is conserved, both sides, and few quantum numbers that I not go in details, because in particle physics, not only charge are there are other kind of charge in particle physics called color charge, like strong interactions, color charge, weak interaction charge. So anyway, the charge has to be conserved. Now you tell me, when T is much higher than ME, then even photon is massless, but it's there. When T means they are equilibrium, that means E plus, E minus, and gamma, they are all having common temperature T. When you can achieve equilibrium, when both reactions are equally possible, up, left and right. So now, you tell me, even if the mass of the photons are 0, but still it can produce heavy mass particle. What is the mass of the electron? Who can tell me? Mass of the photon is 0, and mass of the electron and positron, they are the same. Particle and antiparticle has same mass. How much?
9.31 into 10 power minus 30 kilograms.
No, I want in electron volt. Yeah, that is the natural units for particle physics.
0.5.
Huh?
0.5 MeV.
Yes, almost 0.5 is 531, but I am just writing 0.531 MeV. MeV means, 10 to the power 6 electron volt. In particle physics, we write the mass in this term. So see, E equals to mc square. So m can be E by c square. Now in particle physics, we take natural unit where c equals to 1, h cross equals to 1. This is called natural unit, and Boltzmann's constant equals to 1. And we will come to that later. So E by c square. So that means if something has a mass electron volt, C is 1. So we write m is equal to electron volt. But actual mass is electron volt divided by C square. But if we divide it by C square, it will be a very small number. So we just say mass is 0.531 MeV, but actual mass is divided by C square. Okay, so this is a natural unit. So now you tell me how long this process, both sides, forward and backward, will continue. How long? Because forward will continue anytime because it's heavy mass producing zero mass. It can continue. But this side will be slowing down to produce heavy mass particle when the temperature of the photon or the temperature, like the common temperature T, becomes less than m electron. And we know that temperature of the universe is falling as 1 by A scale factor. We have not proved it, but you have to trust me, we'll do it. And you'll give you an homework actually next class, you'll do it, thermodynamics lab. So as A is increasing, T is decreasing, and at some point T will come below. I'm just taking an example. There can be many such reactions. I'm just taking one example. So T will come below electron mass or positron mass. Then what will happen that time? Can you tell me? After when T falls below, then this reaction can happen efficiently, the reverse reaction? Yes or no?
No.
No. The answer, why?
Energy not sufficient.
Because you see, E comes from not from photon mass, photon energy, m is equal to 0. So E, you have to have more energy to produce this if you have to go, or at least equal energy. So E gamma is square root of m square c square 4 plus p square c square, but m is 0. So E gamma is Pc, and P is momentum, and it is almost P is equal to T in practical physics. There will be some constant. So when the temperature is less than Me, so C is 1. So basically, if you have C equals to 1 here, then you have E gamma is almost equals to P equals to with some constant T temperature. Temperature also we write it in electron volt. So now if temperature falls even below, then momentum falls even below, that energy falls even below, goes down. So you cannot create because you don't have enough energy, because energy has to be conserved. So charge has to be conserved and energy has to be conserved. Then we only that two are needed. Conserved. Is it clear for everybody?
Yes, sir.
That this is very simple. When temperature drops below the mass, right hand side does not have enough energy to create the left hand side. So then what will happen from that moment onward? Who can tell? So step 1, this and this, both forward and forward and backward. Both are efficient. When T much less than, greater than Me. Step 2, which I just told. When T falls below Me, what will happen? Which one is efficient? And which one is less efficient? Tell me.
Electron, positron to gamma, photon is more efficient.
Backward. So only this one will happen. Only this, gamma plus gamma. So what will happen? The number of electron density in the universe will keep going down and down and down. True? Because they are producing more photon. Yes? But photon are not able to produce electron. Yes?
Yes, sir.
Yes, sir.
And if it continue, then what would happen if continue like that? There will be no electron today. But that is not the case. In cosmos, we see so many electrons everywhere. This is true for another thing. I'm just telling you. Similar process has happened for dark matter. Dark matter, I'll do it a better, like proper introduction to dark matter on the last class. But dark matter are called WIMP, weakly interactive massive particle. Weakly, they can have weak interaction, interactive. They don't have charge, and they're heavy mass particle. Why? Because they are cold today, non-relativistic. If they are relativistic, you cannot form. So what is dark matter? Dark matter is, suppose this is your galaxy, Milky Way, to almost 2D, because the thickness is very less. Thickness, the diameter is much higher. But the dark matter halo will do it much better. It's like a sphere. And they're like a cloud, but we're made up of heavy particle. We know that dark matter is 26%. We have done it, but we don't know what it is. And this is like an egg, almost like a dark matter sphere, halo sphere. It is called halo of dark matter. Halo sphere made of dark matter. And inside, like a disk, is your visible galaxy. And it is shown that without this spherical halo, you cannot actually sustain the stability of any galaxies you see. So dark matter is there like a halo. Now the particles, we know that it has to be heavy. Heavy means in particle, HEAVY, it's in particle physics, it is called cold. Cold means what? That means mass of dark matter chi is much, much higher than the temperature of the universe. So that means its energy is actually, suppose rho dark matter is number of dark matter, number density times energy density, but energy is just mc square, because the momentum part is 0, because mass is much, much higher than temperature. It's a non-relativistic particle. But C is 1, so rho is basically m chi. Chi is the dark matter, n chi. This is the dark matter density today. Okay, this much enough for today for dark matter. We know that there is a good amount of nx, and when you multiply it, we get the dark matter density, and when you divide it rho by rho critical, we get around 0.26. We know that 26%. So there is a pretty good amount of number density of dark matter around our galaxy, around galaxy cluster is all over the universe. Supercluster, even in the megaparsec scale and even in the horizon size, there is dark matter too. Okay, we'll do it later. So now for dark matter also, so here you remember the step 3 is going to happen. We don't discuss yet, we'll do it, because there will be no electron, but actually in reality we see there is a lot of electron. Clear? Yes?
Yes, sir.
Okay, very nice. I want a different color. How to do different color? Let's do it for dark matter black. So similarly, I'm doing it for dark matter. Is parallel thing. It has nothing to do with electron, positron, and gamma gamma. So dark matter is chargeless. So there will be 2 dark matter particles colliding in early universe, step 1, when the temperature of the dark matter, this time temperature of the dark matter is much, much higher than the mass of the dark matter, because early universe is very hot. Now dark matter particle can weakly interact with standard model, and it can create many such particles like Q and Q bar, quark and anti-quark, or it can create, say, electron and positron. These reactions are allowed, but it has to create in a pair so that the charge is conserved. So dark matter can annihilate in early universe in many channel like this quark Q bar, or the same dark matter can go E plus E minus. So they can produce, these particles are called in particle physics standard model particle. Means the known particle of standard model which has got a discovery of each particle got one Nobel Prize. Standard model particle. CLE. So, for example, I now don't make complicated all the things. I'll just do it with the sorry. Let's do it. Clear drawing. No, eraser. I have to do. Let's do this example. It is going to Q1. This quark and anti-quark. Okay. Now,
So,
yes.
that means two dark matter particles can annihilate to form a quark and an antiquark.
Yes, yes.
Okay.
Yes. It can create positron and electron. It was doing it early universe. Okay.
Okay.
Mm-hmm. So so now the same thing will happen when the step 2, when the temperature falls below the dark matter mass. Then what will happen? Which reaction will happen more and more? Tell me. Dark matter will annihilate to which particle? More? Sorry, this is not the dark matter mass. Yeah, the temperature is much less than dark matter mass. So that means the quark, see, the mass of quark or electron or positron is very less than dark matter mass. Okay. So if they have to produce some, say, for example, I'm giving an example, Q plus Q bar. If Q and Q bar has to produce dark matter and two dark matter particle, it has to come from momentum. You see, energy has two parts, mass part and the momentum part. But as mass of quark is much less than mass of dark matter, so you can only produce heavy dark matter particle if you have enough momentum. Is it clear?
Yes.
But now the momentum is less because T has fallen below mass. So you don't have, and T is basically P, I just said. So you cannot create back dark matter. So it is similar to like that. Heavy particle will annihilate to light particle, but light particle will not be able to produce back heavy particle in the second step. So the number of heavy particle, here electron vanishing to photon, here dark matter vanishing to quark, antiquark, or electron, positron, or neutrino, other particles. Dark matter. So dark matter will start vanishing more and more and more and produce all standard model particle, but conserving charge and energy. Is it clear?
Yes, sir.
Yes. So then what will happen if it continue? It's like electron and positron. If it continue, then what will happen?
There will be a time where there will be no
There will be
dark
no
matter.
But we see there is a huge amount of dark matter in the universe. Like we also see there is huge amount of electron in the universe. So then some magic has to happen in the step 3. Yes? Who saved us? Magic happened. Because otherwise there will be no dark matter, there will be no heavy particles. There will be no electron, positron. Will only end up in very light particles called photons or neutrinos. But for making galaxy, we need quark. For making galaxy, we need dark matter. We need electrons. Stars need an electron. So what saved us? That is the third step. Very important. The third step is very conceptually, it is easy. Analytically, it's a little tough, but I'll give you the analytical. Conceptually is, see, the gamma, the rate. Gamma means the rate. A rate of annihilation. Annihilation means when two particles come, say electron plus positron, and go to gamma plus gamma, it's called annihilation, two body. So this gamma in particle physics, gamma annihilation is given by the number density, because if the number density is more, then there will be more annihilation, times the cross section sigma times velocity of the particle. See, if velocity is more, then there is a high chance they will collide. But if they are very slow, they don't come at all, then there is a low chance. So it is proportional to velocity, and of course sigma. Sigma is the cross section, like you calculated in quantum mechanics or in many things. Is sigma is cross section, and cross section is a particle physics process. I will not do it in this course because this is a particle physics process, and those who are interested, if they have to learn, it's called Feynman diagram. We don't do it here. It depends. It have to take a quantum field theory course. But whole Switzerland CERN is basically they calculate sigma for different processes. Higgs bosons production sigma, quark production sigma, and so on. And they can be exactly calculated by using Feynman diagram. And then if you know the number density, then you know the annihilation rate. Means at what rate the energy is disappearing. N times, or number density is disappearing. So if there are more particles, why it is proportional to n? Because if there are more particles in a box, more number density means more particles, then the chances of collision is higher, and they will produce more more photon and photon. It is true for dark matter also. If there is more dark matter density, they will produce more quark, antiquark, or electron, positron. And this is the gamma for forward reaction. Forward means only dark matter going to chi plus chi. Oh, sorry, I'm doing it for electron. Electron plus positron going to photon plus photon, which is true for same for dark matter also. Going for other particle, but it has to be, say, quark, antiquark, or other particle, as I said. It can be many more channels. So now something happens. If it was a classical mechanics or thermodynamics, what was happening? The box size will be constant. But in cosmology, the box is, who can tell me? The volume is increasing. So if you wait for some time, the scale factor become double, 4 times, 8 times, 16 times. And scale factor was very small, as I said, in early universe, 10 to the minus 40 or 50. A. Now scale factor today is A equals to 1. So huge change in scale factor. So there will be huge change in volume. If you take any unit volume, they will become bigger and bigger and bigger, because every direction X, Y, Z, things are changing. X, Z, and Y. It is stretching. So if the volume is stretching, increasing, number density will increase or decrease? Decrease. So what happens in cosmology? V increases volume. So what happens is, at some point, this is the step 3. At some point, the number density is so small, they don't find each other. And in bracket, it is effectively. Once in a while, they will find effectively. They find each other to collide. Suppose you are in Pondicherry University Physics Department. When all the classes are full, all the things are happening, then you collide with your friends, or other people, they come closer to you. But in Corona time, when the things are very less, you don't see people around you. So you cannot even talk or interact with them. Yes? Number density has gone down. Exactly like that. When volume becomes bigger and bigger, when number density becomes so less, this gamma drops, and the comparison is this part. You have to just take it from me. I cannot prove it now. This happens, means this is the what I have written is mathematical part is when gamma becomes equals to the h, because h is expansion rate. We know that dot by, and gamma is annihilation rate. When h takes over gamma, means the expansion rate takes over annihilation rate, they effectively cannot annihilate into each other because number density drops below. And from that moment onwards, this forward annihilation stops also. And electron and the electron and positron number density does not vanish to zero. So it is, see, the expansion of the universe has saved us. It is almost like it was planned from the beginning of Big Bang that expansion is needed, not only for galaxy to form, we just told you, for stars to enter our horizon, but expansion is also needed to make the particle be there. Otherwise, they will all vanish into the smallest mass particle or zero mass particle. Clear now? Yes?
Yes.
You have to read it in Coleman Turner book and all this thing I'm giving you, because in one class you cannot understand all the things. So now, what is happening here is this. So as for example, as E plus and E minus, this process now, gamma stopped effectively. Once in a while, the electron will find a positron. That's by chance, random. They will find once in a while. By chance. But effectively, they will always bypass without hitting each other because number density is. Like, suppose the number of people in Pondicherry physics department is so low that somebody will be passing through one staircase, other people will be passing through the library, but they don't interact with each other. But once in a while, you can still interact. Okay? Yes. Yes. So now, this process stops, but does it mean the number density is constant or not? Who can give me the answer? Because now the annihilation stopped and the reverse process has already stopped because there is not enough temperature. So, number density will be conserved? Not conserved. Number density will be constant or it will change? Now onwards?
It should decrease.
It should decrease because of
Expansion.
Exactly. Because the volume is becoming bigger and bigger still. So in cosmology, the number density before, this is the volume is becoming bigger. Number density is nothing but n by v. N is the total number of particles. Yes? Now total number of particles now onwards is constant because there is no annihilation, but v is increasing. So n will still go as what? Who can tell me? 1 by aq, because v goes as aq scale factor. Yes?
Yes.
But this a factor, scale factor, say from matter dominated universe till now is only 1,000 times when this thing happened, means when this thing stopped, or say 10 to the power 6 times, means it's not a very huge suppression. But if annihilation would continue, if this process would not stop, the number density goes as e to the power minus mt. M is the mass of the electron, or for dark matter case, it is the electron number density, E minus. For dark matter, it will be e to the power minus m chi t. And this exponential drop is huge. So there are two ways number density can go down. One is background expansion, it's like 1 by a cube, plus in the early universe, it was annihilating exponentially to particle. So is it clear now? Two-way number density goes down. early universe in the stage 2. In the stage 2 means this is the stage 3 when this stopped, but stage 2 was when this was only happening. So number density, why it is e to the power minus mt, I will not discuss it. It is from particle physics, but it is called non-relativistic Maxwell's Boltzmann distribution. It comes from there. You know that, no? Maxwell's Boltzmann distribution exponential. You know that? E to the power minus something?
Yes, sir.
Yes, so that's why you get this, because it's a non-relativistic distribution. Why non-relativistic? Because I have told you, because the mass of the electron is much higher than the temperature. That is the condition that sorry, this is not the step 3. I'm all talking about step 2, when the annihilation was happening. That time m electron was much higher than the temperature. So it's non-relativistic. In non-relativistic, you get a Maxwell's Boltzmann distribution, MB. So you get e to the power minus m chi t. I'm sorry, I'm mixing it up. Here I'm writing electron, but I'm writing it. But you got the idea, no? It can be true for any particle, yes? Either dark matter annihilating into light particle or electron annihilating into photon. Yes? Clear?
Yes, sir.
Yes,
So
sir.
now, in cosmology, we define, you'll know why I'm defining, called co-moving number density, which is nothing but number density n times a cube. This is called co-moving density. So I multiply it by a cube. So now you tell me it is called co-moving number density n co-moving. Co-moving means you nullify the effect of expansion, because n is going as 1 by a cube. So I'm multiplying it n times a cube. So it will become like a constant when number density dilutes only because of expansion. Is it clear?
Yes, sir.
Because it is going as 1 by a cube. I told you when annihilation stops in the steps 3, when Hubble expansion takes over. So if I plot this co-moving number density, I'll tell you this is what happens. In the beginning, also when they're relativistic, both sides are equal. Step 1. So the co-moving number density, it can be shown in relativistic is it drops very slowly. This is I'm plotting the n co-moving versus a. Okay, time. A is time basically. And then this is stage 1. And then suddenly why it is dropping very slowly here, because the forward and backward reactions both are effective. So you are producing, say I'm now plotting say E minus or E plus. You are producing electron and positron from photon also. So it is small. Then when the backward process stops, then only forward, then it exponentially falls off like that. Sorry, exponentially like that. This part is not right. Exponential falls off happens. This exponential falls off goes as e to the power minus m. Actually, not mt, sorry, I was writing wrong. It is m by t, dimensionless, sorry. We'll derive it next time. E to the power n by m by t. Now, as m is much greater than t, so it will be e to the power minus 10 or minus 20, like that, very sharp cutoff. And if it have continued, then you hit the 0 very soon. But then again, when the third stage happens, this is the first step, number 1. This is the first phase. This is the second phase, when only the forward happens. And then what happens? How this plot will look like? Who can tell me? Ravi, you don't tell. Now the co-moving number density is what? I have just told you.
It will be constant.
It is constant, so it will become. And this density is called n freeze out density. Freeze out means if it was going down and suddenly it frozen and it remains like that. and it remains constant. That means when freeze out density, when n co-moving is parallel, constant, that means know that annihilation has stopped, particle physics process has stopped, only the co-moving density is constant. That means actual density is just falling off as 1 by a cube. Clear?
Yes, sir.
So this is true for dark matter also. If you see any modern dark matter graduate level lecture, they will first do like that. The number of co-moving density. There is exact differential equation for that. That I am not doing. It is falls very slowly, then exponential. Sorry, this will be exponential, and it will continue to 0 today if Hubble will not save, and then it does not come like a sharp break. It comes like a smooth and then become constant. This density today n matches to rho, because n, if you know n today, n co-moving, n not co-moving today. So this is not n, this looks like something else. This dot line today is the n naught. Let's call it n naught today. So dark matter density will be n naught times m pi, and n naught is nothing but it's co-moving. So it will be n naught by a cube times m chi. You can call it m chi naught, some constant. So rho dark matter today is not today. It goes like n naught m naught by a cube, and today is nothing but a is 1, so n naught times m chi naught. N naught m chi naught, and this thing we can exactly calculate by solving when this Hubble expansion gamma was h, and gamma is nothing but n times sigma b, and this sigma we calculate from particle physics. So one thing is still needed to calculate is n, that is the next step today. Is it clear now? So, and h, you know how it goes. H is a square is equal to 8 pi g by 3 rho radiation. These are all happening in RD universe, rho radiation. Okay, so you know how rho radiation goes. We'll do it today. So depending on the photon, neutrino. So you know h, you know n, you know sigma. Then you can calculate when gamma equals to h, and that will give you a value of a freeze out. This is called f freeze out. That means at what a, this I'm plotting a f, this constant thing happens. So given a particle physics model, you can actually tell that when the freeze out happens, that means when the things came out of cosmic equilibrium because it was falling off with the interaction and it's decided not to interact anymore and started behaving in its own territory and not interact with each other and only diluting as 1 by a cube. Is it clear now? Yes? Any question?
Sir,
Yes.
so how do we know about these dark matter interactions? If they produce matter?
That you need to depend on the model. It is a model independent thing. There is a model for WIMP dark matter. It comes from, it is called supersymmetric dark matter. So you have to have a particle physics model of dark matter and then only you can calculate. So I'm not telling that this is what dark matter is because nobody knows what it is. But there is a high speculation that dark matter is WIMP. And if it is like that, then its production or its freeze out density will be like this. Otherwise, there will be 0 WIMP today. So in particle physics, when you go, they will exactly tell you what is the cross section. You have to do a quantum field theory and supersymmetry course for that. But it is possible. Okay?
Yes.
It itself is a 6 months and plus 6 month 1 year course. Quantum field theory one semester and supersymmetry 1 semester. If you are interested in particle physics, then you should join your PhD in TIFR or HRI or IISc. They always calculate, or ICERs, many ICERs, they always calculate this n times sigma v from Feynman diagram. Okay, so now what I'm going to do, my writing part is over. I'll share a note. What I have been telling, I'll give you this note. So now, as I tell, that we'll work in the natural unit, H cross C KB equals to 1. And there will be some conversion in natural unit. You should know it. You should Google it, what is natural unit. Okay, it's much easier. So in natural unit, you see the proton mass, the Planck mass is GeV. So Planck mass, the mass of a particle is not gram, it's in electron volt, GeV. Okay. So now in natural unit, if you write this Hubble equation, H square equal to 8 pi G by 3 times rho, in natural unit, 1 by 8 pi G is m Planck square. That you can see from here. That is, I'll give you the note. Okay, that is your homework. So the gravitational constant can be written as 1 by m Planck's constant. So basically your Hubble equation become rho by m Planck square. So now I'm skipping this. This you keep it in mind, that H square can be written either in terms of Newton's constant or in natural units it goes as rho by m Planck square. And how to go into natural units, the description is here. I'll send you the note. But also you should search from Google and natural units. Very easy. Now, as I said, I'll come to that later. I need this. Where is that? Sorry, again. So this is the condition. Gamma is equal to n sigma v, and it is equal, not greater than. Early time it was equilibrium. When H takes it over, then n sigma. Now n I need to find. Sigma will be given by particle physics. And early universe, the velocity is, though even if it is non-relativistic particle, but velocity is maximum 1/2 or 1/5 of speed of light. So you can take v to be c, and c is 1 in natural unit approximately. By a factor of 2 or something will be different. So it's basically n times sigma, because it's very early universe. Okay. Are you all following me?
Yes, sir.
So now, how to calculate this n? The number density in equilibrium, because they were in equilibrium. And then the H takes over and it comes out of equilibrium. But before that, n is equilibrium. So when you equate n times gamma equals to H, and gamma carries number density, you need to find number density for it. So for that, I'm coming here now. This is what it is. I was telling you from StatMech. So when particles are in thermal equilibrium, for example, this gamma electron, they are in thermal equilibrium, they have a distribution function f of pt. And this f of pt is nothing but this is. For Fermi-Dirac, it is, there is a minus 1 to the power 1, where this is the Fermi-Dirac distribution function, 1 by e to the power e minus mu by t plus 1. And for Bose-Einstein boson particle, it is minus 1. Do you know that?
Yes, sir.
Yes. So now, for our purpose, you know that for photon mu equals to 0. Yes?
Yes.
If you know it, then this is your homework. Okay. But even if some other particle, say for example, neutrino will be doing it, or other particle, the energy is much higher than mu in early universe. Early universe is a very hot plasma. So for cosmology purpose, mu can be neglected. So your distribution function is e to the power e by t plus minus 1 whole to the power minus 1. So now, let us get back here. Number density. I'll come to that later. Number density. Say how to calculate number density. For example, I want to calculate number density of photon. So I was just saying it is an integral of dqp times f of p or f of e. Now energy of photon, the average of energy, because many particle has many different distribution function, no? So you have to do an average. That also dqp, there will be a g by 2 pi q. That you should know it from statement. G is called degeneracy factor. Okay, this comes from distribution dqp into f of p, and whatever you are averaging over, you have to multiply it here. And if you are not averaging over anything, set only the number density, just is the integral over dqp f of p. It's like a probability function like that. So here you are averaging over energy. So each energy of each photon is p times c. Is it clear? Yes?
Yes, sir.
This you should do it from, this is called rho. Energy or average is called rho, energy density. And this is the number density. So now take your pen and paper and follow me, that what I am doing. I don't want to do the full integral, but I want to find how the number density or energy density goes as a function of temperature. Okay, so let us take the number density. Oh no, let us take the rho for photon. I generally ask this question in PhD interview. Without even doing the integral, you can tell. So g by 2 pi q, let it skip. dqp 4 pi, it will be like 4 pi p square dp. Yes? dqp in the 2 sphere 4 pi p square dp. And f of p is how much? 1 by e to the power, can tell me for photon how much it will be?
PC by T minus
Huh?
1.
No, tell me in terms of photon. I just said for photon, it will be e to the power e, mu is 0. So e by t minus 1 and whole thing is below 1 by, isn't it? And in natural unit, kb is 1. kb means Boltzmann's constant, c and gravitational constant, they are all 1. So it is very simple in natural unit, e to the power e by t minus 1, isn't it? Confused? What is the number density I just told in the last in this thing? See, g by 2 pi cube. This one I am doing g by 2 pi ep f of p dqp. Ep is pc, isn't it? For each particle energy, you have to multiply and then do the integral. Yes.
Yes, sir.
Yes, sir.
Then f of p is what? Go back here. F of p for photon, mu is 0. So e to the power e by t minus 1 and whole thing is 1 by. No, there is a minus 1 in the top. To the power minus 1. Is it clear?
Yes, sir.
Very simple only. So particle physics units are a little bit different, but it is easier here. Sorry. So now e to the power e is how much? P, pc. Yes.
Yes, sir.
And c is 1, so it is p by t minus 1. Now this is the integral from 0 to infinity. Now suppose what do people do? They want to tell that how this rho goes as a function of temperature. For that, you define a quantity called p by t is x. It's a new variable. So with this new variable, it will still become g by 2 pi cube. Oh, sorry, this is not right. This 2 pi cube is below. G by 2 pi cube. The integral limit still remains 0 to how much? Infinity only, because t is not infinity. Okay, so p goes to infinity. Now it becomes 4 pi. What is p square now? In terms of x? T
Sir,
square.
one more P will be there or not?
Huh?
EC is there for energy.
It will be P cube.
P cube.
P cube.
No, I'm coming there. T square times x square. And yes, at least the first part is that 4 pi p square is like this. Yes? dp is how much? T into dx. Yes?
Yes, sir.
T into dx. And then there will be another pc. P is basically x times t. Yes? Divided by e to the power x minus 1. So now if you take all the t out, so it will be g by 2 pi cube, because the integral does not depend on t. So how much t will come out?
T to the power 4.
Very nice, t to the power 4. Then there is an integral 0 to x, 0 to infinity, x cube dx by e to the power x minus 1. Yes?
Yes, sir.
Yes.
This function x cube dx, this is called Jitter function. You should look into the note of your StatMech or find out from Google. It is a number. It's called Riemann Jitter function. ठीक है? Yes?
Yes.
So now you can see what is the energy density of photon. Rho goes as t to the power 4, g depending on the number, degree of polarization or degeneracy factor. For photon it is 2, and this is a number, Jitter function. So it's a constant time t to the power 4. And that is what exactly happened in black body radiation. And do you see, I told you that this function x cubed by e to the power x minus 1, it is very similar to the black body distribution, isn't it? Yes?
Yes, sir. Sir,
Before you,
is the integral Riemann theta function or just inside?
Integral is the Riemann Jitter function, not
Okay.
the function. Okay?
Okay, sir.
You
Yes,
do
sir.
it. This is your homework. Tell me what is the Jitter function and how do you get it from your notebook? What is the value? So now we derive that from simple statistical mechanics, rho is t to the power 4 times some constant. And now rho, we know from Hubble equation, if we know, that is why we are connecting StatMech with the GR, that it's nothing but, here I'm taking h square is equal to rho by m Planck square. Now I'm writing the new unit. There will be a constant here, just some 1.66 or something, I forgot. So almost same. A square is equal to rho by m Planck square, rho radiation. Because now rho radiation is this, t to the power 4. So h square will go as t to the power? Tell me. If you use this rho radiation from this calculation I did, it goes as t square, sorry, t to the power 4. So h will go as how much?
T square.
Square, exactly. So now, let's go back. What I have done, that's what in the note. See, h is t square by m Planck square. T to the power, h square is t to the power 4 by m Planck square. And there will be some small number of, that is your homework. There will be some, because Jitter function will also enter here, because you have substituted rho. But Jitter function value, all these things when you enter, then you get, let me go. So this is what the Jitter function you will get. Rho is 1 times pi square by 30. This is the Jitter function, okay? G something like that. Not pi square by 30, some 1 by 30 will come, because before there was 1 by 2 pi cube was there. So you will see it, what is the jitter function. The jitter 3 by pi square, which is like this. That is your homework, I am not giving you. Jitter 3 is 1.2. So that you have to do, and I am just going to tell you, this you should remember. Rho r is pi square by 30 g star t to the power 4. G star is the degeneracy factor, okay? So please write down in your note this part. Later part, forget about this complicated G star, I'll tell you later. So just pi square by 30 t to the power 4 times g. And this pi square by 1 by 30 comes from jitter function and all these things. After doing 2 pi to the power 4, 2 pi cube term was there. So this is your homework, you have to show me and send me by PDF copy. Clear? Yes, I have already done the things, but you have to now fill in all the constant and everything. Is it okay now? Yes?
Yes, sir.
So now you see rho r goes like t to the power 4, and rho r is nothing but h square. So h square goes as t to the power 4, so h goes as t square. This is a very important thing we have found today. H, Hubble parameter, goes as t square in the radiation dominated universe. Okay. And you will see that now when we want to equate, now forget about all this thing. H is t square by m Planck. N goes as 1 by a cube, and it goes as t cube. Or a goes as 1 by t. But I can also derive it for you, how n goes as t cube. It's the same thing, what I did here. See, now if I want to do it for n, this PC term will be not there, right? Just the number density, because rho is the number density times energy density. So that's why you multiplied by PC. Is it clear?
Yes, sir.
Yes, sir.
So if you now do the first integral, everything will be same except PC will be missing. So tell me now, the n will go as how much?
T cube.
T cube, because one p will be missing, and every p will give you xt term, and x will anyway enter in jitter function, but t will be 1t will be less. So rho n goes as t cube. So that's what it is. Now see, with StatMech, we are getting all these things. N goes as t cube. So now we are actually ready to do the calculation now. N sigma v average is h for any process, and n I know goes at t cube. H goes as something t square by m Planck. There will be actually a factor of 1.6, something like that. I know that. That you will do it times g times g, that g factor, degeneracy factor. So now sigma v is 1 almost. Sigma is a particle physics process. So now I'll give you one homework number 2. First is to do the jitter function and find out of the homework number 2. It is called neutrino decoupling in early universe. So neutrino was also in thermal equilibrium with a beta decay process. Okay, beta decay kind of, it's called weak interaction. Neutrino was in thermal equilibrium, and at some point, the sigma neutrino becomes such that that this condition is achieved and it decouples. So basically, neutrino was in equilibrium with electron, neutrino, and photon, and also G bosons, W plus minus. I'm not writing. So electron and neutron, beta decay mein electron and neutron and photon and neutrino involves in the reaction. You remember beta decay? Yes. What is beta decay? Anybody can tell? You don't know, no?
proton
Ha.
emitting neutron with neutrino, or neutron into photon emitting neutrino.
So tell it again, proton plus photon. Or just proton going into
So proton going to neutron,
neutron plus
positron
positron, very nice,
plus anti-neutrino.
anti-neutrino. So if you do it in another way, say like an anti-proton or neutron going into a proton plus electron plus neutrino, isn't it? Yes. If you take it to the other side, so this is also can happen, reverse of that. In particle physics, reverse can happen. It's proton, if this can go, so if you change the side, then it becomes electron, and then anti-neutrino becomes neutrino, something like that. Yes? Yes? So now just know that they are the equilibrium. That means neutron means it has quark. It has quark. So they are in equilibrium with electron and photon. And electron interacts with photon through quantum electrodynamics, or you know that Thomson scattering, or we haven't done it already, CMB. So they are all in equilibrium. Then at some point, this cross section of neutrino, I'll tell you it is GF, some constant, GF squared, T squared. This is from particle physics. I cannot derive it here. Okay. So if you put it back here, then it will be GF squared T to the power 5 time is equal to 1.6 times G something, G star times T square by M Planck. And you will find, if you equate it, then we will find the T decoupling of neutrino. Yes, by solving this equation. Because now you have all the ingredient. I have given you how sigma goes. Now you know TQ, N goes as TQ, and now you know H how as a function of temperature is goes. Clear? And you will find out, this is your homework, that this happened at a temperature T. What is that temperature? You find out from your calculation. Next class we will do it, but this is your homework, neutrino recovery. It will be very close to MeV, and the time wise, it will be 1 second. So when universe was 1 second old, neutrino come out of proton and neutrino and photon, and neutrino starts going as non-interacting particle neutrino, just interact among themselves, and they expand. So their co-moving number density, N co-moving, become constant. Okay? And they don't interact with our standard model particle. And these neutrinos today is called, like CMB, they are called C nu B, cosmic neutrino background. Like photon got decoupled from electron and proton at 13.6 here. Now we know it is 0.1 electron volt from last class. Like that, it happens, CMB happens 1 million year. But C nu B, cosmic neutrino background, happens at 1 second. But we are not yet detect neutrino background, because detecting neutrino is very hard. But in next 10-15 years, that is the plan. Like Planck mission, we will do a mission to see the whole universe from 1 second by a neutrino sky. For that, you need neutrino detector in the satellite. Okay, is it clear now?
Yes, sir.
So now you know which equation to solve to find out the freeze-out equation for neutrino decoupling. 1 second, that is your homework, by the way, this one. Calculate, you find the value of G Fermi from internet. Solve this, what is G star, you can take it from internet, find the T. M Planck value also you put in electron volt. Then you find the T in electron volt, what will be. And then from temperature, you can always map back into second, because earlier is the higher temperature, lower is that there is a converter in internet. If you give the temperature, that will give you the time. And that you should find that it should be of the order of 1 second. Is it clear now? Yes?
Yes.
So today's class, we did quite an interesting thing. So you now tell, I have spoken a lot. I have been speaking from the morning. Okay. So this is the time to our rituals every day. You know that. What is the rituals? Who can tell me? Yes. Hello.
Turn the video.
Turn on the camera.
Turning the video on. We should, in this lockdown, we should show our faces. Okay. Even if it is tough, you can show a little bit smile. Okay. Other people turn on the video. Okay, very nice. Today, Srivardhini also for continuously turning on the video. Okay, very nice. So now you today learn what are the things you learned today? How dark matter, you heard a little bit about dark matter and how they are produced. Yes, what else? We have learned that how neutrino can be decoupled. We have learned how electron and positrons number density is saved, not zero today. Yes, these are the whole thing we learned today. What else? Now we can turn off the video. And what else we learned? You tell. The concepts, then we are done. How to calculate number density in thermal equilibrium. Yes, we have done it for boson today, but you can do it, we'll do it for fermion also later. Then the only change will be plus. From minus, there will be a plus sign. Yes? Anything else? Why the freeze out happens?
Because as universe is expanding, there is no more collision to.
There is not enough particles to collide. Okay? So that's why dark matter cannot find another dark matter efficiently to produce standard model particle. Anything else?
Expansion important to keep the density constant.
Moving density. Yes.
Yes.
Otherwise, we'll end up in only photon today or neutrino. Yes. And you cannot form galaxy out of photon. So ultimately, you will not be here again. So in this class, many times we have proved that things has to go right for you to be here. Yes?
Yes, sir.
Starting from cosmological constant and all these things. So that's why cosmology is a very interesting topic. You give some constant number and laws, and I tell you what will happen. And then it's realizing that if you change the fine structure constant or little bit cosmological constant number or this Hubble parameter rate, little bit, you'll not be end up producing life. So actually it is a little bit fine-tuned system. That's what the understanding is going at present time. But kuch fine-tuning hai and kuch prediction we have. Not everything is fine-tuned. That's why it is beautiful. You give some few fine-tunings and then you say, okay, now look for cosmic microwave background. Now look for dark matter surge. Now look for dark energy density. So science is mixture of both. Some part you assume and you say this is what it is. There is no explanation for that. And using that, you explain and you do many things. So if some scientist tell you, I understand everything, definitely he does not understand the assumption. Because the answer, for example, speed of light, c. You cannot say why speed of light is c. Yes, right? Making sense? Hello?
Yes, sir.
Because have you ever read any explanation why speed of light is c? Yes or no?
No, sir.
That is the assumption. That is the starting point. And then with that, you can, assuming that you can do many things. E equals to mc square, many things. Lorentz contraction, time dilation, right?
Yes.
So like that, the truth of the universe is, it's like you cannot, it's very hard to question that. It is an assumption. So you have to somehow digest it, and then from there you can do a lot of calculations. Okay, right. Very nice. Anything else we did today? You remember that when the reaction happens, what has to be conserved?
Charge.
Charge and energy.
Charge and energy. Yes. Very nice. And even if the mass is low, but you can produce heavy mass particle in collider or in RD universe by using what?
Accelerator.
By no, that is in lab, but RD universe by using the momentum term, p squared term, isn't it?
Yes, sir.
That's the thing. That's why a photon, which is zero mass, producing 511 keV electron. That's the magic. It produces that, okay? But as long as momentum is available, temperature is high. When temperature drops, you cannot do that. Anything else we did today? So thermodynamics we done. Jitter function, yes? That is your homework, yes? What is that value? Zeta. That integral x cubed by e to the power minus x, e to the power x minus 1. Very good. So today's class is very interesting. We are merging GR with thermodynamics as well as particle physics. Okay. And what is your homework? The Jitter function integral. And what is the homework number 2? Tell me.
Neutrino decoupling.
Calculate that freeze-out equation for neutrino. I have given you everything and find out that it happens at 1 second. Or the temperature. And temperature, once you know what is the time. Very nice. So, and then we have talked about cosmic neutrino background. Yes? Very similar to photon decoupling. Photon also came out of electron and proton-neutron ionization. And first the 13.6 electron volt, but we discussed last class that it is not 13.6, it can be a little bit lower, 0.23 electron volt, because the tail of the Planck distribution function has higher energy. Ultimately, it needs 13.6 electron volt, but even if the mean of the distribution function is much lower, the tail has a higher energy, and we discussed that the number of photon is almost 10 to the power 9 times the number of proton in the universe. So even in the tail of distribution function, you have enough photon to ionize the number of available atoms. You remember from last class? Yes?
Yes, sir.
That's very nice. Very nice. So this much today. Already a little bit today, a little bit less concept. I did a lot of calculations and all these things. Next class, we'll be doing a little bit more deeper into it, the thermodynamics and a little bit about entropy. And from there, we'll do one more interesting thing, that why that neutrino temperature today is different than CMB temperature, and the factor is just a little bit. CMB temperature is 2.7 and neutrino temperature is around 1.9 Kelvin. This we will derive next class. So once we discover neutrino background, its temperature will be 1.9 Kelvin, not 2.7. That will be next class. So next class we'll go a little bit deeper into this freeze out and neutrino temperature and all these things. And then the last class will be on dark matter. So 2 more classes. Great. So you are enjoying this cosmology class? Yes?
Yes, sir.
Yes, sir.
I've learned a lot of new concepts, yes? Very nice. So I'll send you the notes after the classes are over, and then you can read that, and then from there. And if there is time available, then I can give some problems. They are not the homework, but Ravi Bhaiya my student can help you to solve some 7-8 problems in cosmology. Yes, Ravi, you can help them? Yes,
Yes, sir. Sure.
So that then you will know how to do all these things. Very nice. So stay safe. Don't go out for another 15 days. You are not going out, no? Yes?
No, sir.
No, sir.
And that is the only way to stay safe, and you can enjoy later. Okay? Yes?